Welcome back. So, we're in the midst of talking about dynamics beyond diffusion, and specifically, what we're in the midst of is trying to learn how to use rate equations. So, when I say rate equation, in this context, what I refer to is the idea of keeping track of the average number of molecules or members of a population or whatever specific example we have in mind, but we're really keeping track of averages and how those averages evolve over time. So, one of the main venues for this kind of thinking is with respect to the general class of problems that are related to chemical transformation. In other words, so many of the interesting things that we see in the world around us are the result of different members, elements of the periodic table coming together and making new things. And so, in that sense, forgetting things like radioactive decay and fusion, nuclear processes, the total number of atoms is the same, but the total number of examples of nitrogen, for example, in the atmosphere might change depending upon whether those nitrogens get fixed or something like that. So the bottom line is that we have to be prepared to account for chemical transformation. And so in this particular vignette, what we're going to do is we're going to make our first small steps towards this general topic of chemical transformation by thinking about the dynamics of ligand-receptor binding. And the logic of what I'm going to do, I'm going to start out by just talking about the ubiquitous nature of binding problems. And that will be in the context both of just conventional binding, as you already might be thinking of it, but also in the context of enzyme substrate interactions. So I'll say a few words about that. And then we'll take a brief overview of what are sometimes referred to as Langmuir binding isotherms. And this is basically a binding curve and how to think about it. And then what we'll do is we'll turn to a dynamic interpretation of the binding process to make the ligand receptor pair. Okay, so with that as my background, let me begin by trying to channel something from a paper from Jeremy, oops, didn't spell it right. Oh yeah, I did. Jeremy Gunawardena, it's PNAS, and I'm not sure when it was, but 2017 or something like that. And what they were interested in is sort of the universal form that you see on the right, which is one of the things that we're going to work our way towards using both ideas from kinetics and also using equilibrium statistical mechanics. So this equation, it says that the probability of being bound is a function of the concentration of ligand. You can see that in the small ligand limit, this thing is a linear function, and in the large ligand limit, it's saturated. When C is much, much larger than KD, then P bound becomes 1. So this thing runs between 0 and 1. And what we're interested in is trying to understand, as I said, the ubiquitous nature of such binding problems. At the bottom, I show you a bunch of examples of kinetics where there's a similar expression, where in this case, actually, we're looking at the rate at which the enzyme substrate reaction occurs, and you can see that that also is a function, this sort of Langmuir shaped function of the concentration of substrate. And so those two things are going to be juxtaposed relative to each other. Now, just as a quick detour, let's think about the nature of a ligand receptor interaction. So what I have in mind is the binding of, so I have a ligand, and that I'm showing in red below. I have a receptor, and that I'm showing in green below. And together they form a ligand receptor complex, which I show you here. And so we're interested in how that thing plays out. In other words, how does ligand receptor binding work? And intuitively, I would say that this ligand receptor binding can be thought of. Maybe I should just remind you that, how do I want to think of it? So the probability of being bound, I can write that as the concentration of LR over R plus LR. So the denominator here is, let me not do it this way, the denominator is R tot, the total number of receptors. And you might remember from some chemistry class or something that we define what's called the KD as the product of the ligand and the receptor concentrations divided by the ligand receptor. This is an equilibrium idea that tells us about the relative amount of free ligand receptor as opposed to ligand receptor complex. And note that the dimensions of Kd are concentration units, so molar. And if I plug this, so I can rewrite this, I can say that this tells me that Lr is equal to L times R divided by Kd. And so if I substitute that in up here, then I'm immediately led to, I'm kind of doing this poorly. Let me actually copy all this stuff and take it somewhere else. Cut. So I'm gonna add a page here. Just bear with me. Sorry about this, but add a page. So now I can paste this thing back, and we have room to do our business. So this ends up being L times R divided by Kd over R plus RL over Kd, which is equal to the concentration of ligand over Kd over 1 plus the concentration of ligand over Kd. So this is the so-called Langmuir binding curve. And now we're prepared to take a look at the curves here. So one of the things that you'll notice on the basis of this curve is when the concentration L is equal to Kd, then that implies that P bound is equal to 1/2. So that's one thing that we can see from this analysis. So down here I show you 3 different binding curves, P bound, where they have different Kds. So down here you can see 3 distinct binding curves. They all are going to saturate at P bound equals 1. The blue one clearly needs to go to much higher concentration before the receptor is saturated. And on the right, I simply show you that if we use the natural variable of the problem, in other words, this is something we're going to come back to again and again, though we might pipette concentration C, in fact, what the cell cares about, or the receptor cares about, is the natural unit, which is C divided by Kd. That's the natural variable of this problem. And when you plot P bound versus that variable, then we get a universal curve of the form x over 1 plus x. So this is the natural binding curve. Oh boy. So I guess I am once again having some sort of issue here. Let's see. Not sure what happened, but please just bear with me. So this is the natural binding curve. All right, so that's great. So now what we're going to do is we're going to try to attack the question from a kinetic point of view. So kinetic perspective on binding. And I can rewrite this L plus R goes to LR. There's a forward rate K plus, or let me call it K on actually. And there's an off rate which takes us from LR to R. And what I'm going to claim is that we can write the rate at which LR is formed as a decay term. Sorry, the decay term takes, no, sorry, this is a minus sign, so minus K off L times R, and then plus K on L times R. So that is the full dynamics. What's this dynamics saying? It's saying that that there's 2 kinetic processes. One of them is the association of L and R in order to form an LR complex, and that's this piece. Okay, so I guess I could label this with the green, and this is association. And then I also have this guy, which is dissociation. And now I just want to give a little bit of a hint as to how to think about this dynamics and why we have that term that looks like a product. So the way we're going to use these lattice models quite a few times in the remaining vignettes in this course, and the issue that I'm going to claim that there are omega lattice sites, number of lattice sites. So I discretize space. It may seem kind of contrived and artificial, but it captures the essence of what's important, which is the more lattice sites there are, the higher the volume that's available. So I have a certain number of lattice sites. I have a L, which is the number of ligands, and I have R, which is the number of receptors. And I need to find out the probability that a ligand and receptor are in the same box. And so I've already kind of written this down in advance here. So what I'm showing you in this little write-up here, or this little equation, is I want to find out the change in the number of LR complexes in time delta t. So this first term says, well, I have NLR candidates to dissociate currently, and the probability that a given one will dissociate is k off delta t. And so the total number that dissociate is going to be the probability of dissociating, which is this part, times the number of them that are candidates. So that's this decay term. On the next term is the association, and what that says is that I want to take the probability that there's a ligand in my box of interest, the probability that there's also a receptor in my box of interest, and when they're both there together, then the probability of them associating is k on delta t, k on prime actually, because of the units, which I'll explain in a second. And then I have to multiply by the total number of boxes, and the reason for that is that this is the probability a given box is occupied by both L and R, but then I have to actually multiply by all the possible boxes that could occur in. So so that's cool, and you'll see here. Let's see. Well, okay. I'll just write it down. So if I want to turn this into the rate equation, as usual, what I would do is I would divide. First of all, I would say that I divide by delta t, so delta NLR divided by delta t, and then 1 over omega. So I'm now going to divide by omega on both sides. So I have an omega here, I have an omega here. I divide this, and I also need the little volume of the boxes in my lattice. So this volume right here is volume little v. Okay, the volume of one lattice site is volume little v. So, in light of that, let's see here. So I divided everything by omega little v, and that leaves me with, on the left-hand side, I have a d by dt of concentration LR. And on the right-hand side, I have minus k off, and then concentration LR. And then you can see that I'm left, these two omegas cancel out. I'm left with a v downstairs, but I actually need two v's downstairs, so I'm going to put a v downstairs and a v upstairs, and I will be left with k on, and then times L times R, where k on is equal to k on prime times little v. Okay. So what's the point of all this? Well, the point was just to try to motivate where this equation right here comes from. And it's specifically this second order term. The thing I want you to notice is that the units, so let's look at units. This has units of 1 over seconds. And this has units of 1 over molars and seconds. Okay? So the point is that, and that actually is why you can see here, k on prime is k on divided by little v, and my point is basically that the second order rate constant has units not of 1 over time, but 1 over concentration times seconds. Okay, so now we want to next look at this thing in steady state. So steady state. And in steady state, I have that K off LR is equal to K on L times R, which tells me that K off over K on is equal to L times R over LR, which is equal to KD. So we've now got a molecular interpretation of the KD as the ratio of the off rate to the on rate. Okay, so what was the point of all of this this exercise? The thing that I wanted to accomplish was I basically wanted to, as I say right here, I wanted to give you a first example of mass action kinetics. We're going to use this a lot of times. So this is really the first acquaintance that I wanted you to have with mass action, and I'm sure that I will repeat the analysis that I just gave. But let's consider the high points just as a summary. So the high points are that these kinds of binding problems are ubiquitous, and I tried to illustrate that both through conventional binding, such as RNA polymerase binds to DNA or chemoattractant binds to chemoreceptor. But then I also noted that enzyme reactions have a similar sort of structure to them because of the binding of the substrate to the enzyme, whether it's a molecular motor or whatever. I then gave you a thermodynamic interpretation of Langmuir binding. So the idea was that P bound, as shown here, P bound is the ratio of ligand receptor complexes to the total number of receptors. That's what's in play. And using the definition of KD, we're able to achieve a really nice, simple form, the so-called Langmuir binding isotherm. And this is something that we will be able to compute using statistical mechanics later on in the course in other vignettes. We talked a little bit about Langmuir binding curves, and then I tried to write down in a way by scratch and sniff the kinetics of one of these problems, which you see here. And hopefully it wasn't too obscure. The whole detour at the end was just trying to explain the idea of a second order rate constant. And if you like, you can just think of this by power matching, that since the left hand side over here has got units of concentration per time, then K off has units of 1 over time, and here we have a product of two concentrations, and so K on has got to have units of 1 over concentration time in order for the whole set of units to make sense. And I tried to motivate that using this argument about the probability of finding both a ligand and a receptor in the same lattice site had to do with the product of their concentrations, which really it's the probability argument effectively. There may have been some obscurities about dimensions, and I'll try and clean that up probably in a homework. So for now, that's my first pass on ligand receptor binding, something that we're going to refer to quite a bit in coming